This is Giorgia. I ask you kindly to wait for a while because other people are connecting. So we will be back to you in a few minutes. Thanks a lot for keep patient. Okay, good day, everyone. I hope that you can hear me well. It's a big pleasure to be with you today. Just few information before beginning. So just a couple of quick notes. This webinar will be recorded. So don't worry if you are going to enter inside the webinar a little bit later or you might think to lose something. Your microphone are mute, but if you would like to interact with us, you can feel free to use the chat, okay? And we will get back to you as quickly as we can. So, guys, the time is tight, so let's get started. I am Giorgia, and it's a very big pleasure to be with you today. And I've been managing the sales network at Gexcel for the past 18 years. And I'm really, really excited to host this webinar today together with Eleonora, who is an assistant professor in geomatics at the University of Udine here in Italy. And with Eleonora, we've been collaborating for many years. So I leave the floor to Eleonora to introduce herself.
So good afternoon, everyone, and thank you, Giorgia, and thank you, Gexcel, for inviting me and for the opportunity to share our work to this webinar. Let me start with a brief introduction about myself. I'm an environmental engineer with a PhD in industrial and information engineering, and I've been working in the field of geomatics since the beginning of my research career. My work focuses on photogrammetry and LiDAR data processing for the 3D reconstruction of the environment and cultural heritage. In recent years, I've been increasingly working on portable laser scanning based on simultaneous localization and mapping technology, also in collaboration with some colleagues of the robotics lab, particularly for the development of autonomous mapping systems.
Thanks a lot, Eleonora, for being with us today, and many thanks also for the introduction. And Eleonora will walk us through both the technical and conceptual aspect of today's discussion, which focus on documenting complex archaeological sites where access is difficult and the data is often incomplete. So today's goal is to show how UAV photogrammetry combined with SLAM-based laser scanning can help create accurate and comprehensive 3D models. I had the chance to get an overview about this fantastic project in Ancona And what I really appreciate is that Eleonora has shown not only what has been done, but my personal opinion, most importantly, why and how. So I thought, why not offer this opportunity to everyone as well? So, Eleonora, what were the main challenges that you have encountered during this project, and how did you address them?
Well, the main challenge was really related to the complexity of the environments we were dealing with. We had to survey archaeological sites that are often quite large, difficult to access, and with many logistical constraints, and also covered by vegetation often. So in these conditions, we believe that no single survey technique is able to provide both the level of detail and the completeness that we need. So the key challenge becomes how can we reliably document these complex sites? And this is where the idea of integrating different techniques comes in. By combining UAV photogrammetry and SLAM-based laser scanning, we can take advantage of their complementary strength and overcome their individual limitations. And this leads to the aim of our work, that is to develop and validate a hybrid UAV photogrammetry SLAM-based workflow that allows us to achieve both full site coverage and high resolution detail. So let's see how this integrated approach works. Photogrammetry provides accurate geometry and detailed reconstruction of the structures, while SLAM-based laser scanning, in our case using the HERON system, allows a rapid acquisition and a complete coverage of the site, even in complex or vegetated areas. So these datasets are then integrated through point cloud alignment and data fusion, resulting in a final 3D model that combines both high detail and full coverage. So the key idea is photogrammetry gives us detail, SLAM gives us completeness, and their integration provides the best overall result.
Yeah, I can add that I think that what really stands out to me here is the multi-sensor approach. That is, I think, a key point because the integration of different survey technique is the key, because each method brings its own strength, but also, of course, its own limitation. And by combining them, you are not just collecting more data, but better and more reliable information, exactly as you said, Eleonora. And I think that this is what really makes the difference. So, especially in complex environment like the one that you are going to show. So I'd like now to invite Eleonora to take us on a short journey to a very beautiful landscape in Lebanon, where the two case studies that Eleonora is going to introduce us are located.
Yes, well, first of all, let me say that this work is part of the Northern Lebanon Project, that is a joint Italian-Lebanese research initiative led by Professor Marco Iamoni from the University of Udine and May Haider from their third branch, Lebanese University. The project is an ongoing archaeological investigation of the Kura region in northern Lebanon, and the main aim is to reconstruct the ancient regional settlement with a particular focus on the site of Amun and its plain. Moreover, another key objective of this project is the promotion of the regional cultural and archaeological heritage among both the local communities and possibly also among international visitors. And in this context, the two case studies I will show you represent an initial attempt to apply this multi-sensor approach to produce updated and realistic 3D models which can support also future applications like virtual tours and public dissemination. So let's now move to the first case study, that is the Roman temple of Bziza, located in the North Governorate of Lebanon, that was surveyed during the June 2021 campaign. This case study was designed as a testbed to evaluate our procedure in order to document the current state of the site. And at the same time, this case study allowed us to assess the accuracy and the noise characteristics of a commercial handheld laser scanner, highlighting both the advantages and the limitations. As you can see from the pictures on the right, the Bziza temple is relatively small, but is a well-preserved structure with the frontal columns still in place and a single cella. It measures approximately 14 times 9 meters with a height of about 7.5 meters.
Yeah, it's amazing, and of course it's a very challenging site. So I think that now everyone is interested to hear more about the photogrammetric methodology you adopt and how this methodology has contributed to your result.
Well, the photogrammetric survey was carried out using a combination, in this case, of UAV and terrestrial photogrammetry. And for data acquisition, we captured two sets of images, one close to the structure, to the temple, following its geometry, and one at a higher altitude to cover the surrounding area, as you can see in the left picture. Both acquisitions were performed manually without a predefined flight plan due to the presence of several obstacles such as trees and power lines. And in addition, more than 300 images were acquired from the ground with a very high resolution. And as you can see from the right image, this image distribution is quite irregular, mainly due to the vegetation and the narrow spaces, which made the acquisition for sure challenging. Then once the data were acquired, we moved to the processing phase that was carried out using 3DF Zephyr software by 3DFlow, applying a standard structure from motion and multi-view stereo workflow. So we also established a topographic network around the temple, measuring 14 ground control points that were used to constrain the model, achieving an average accuracy of the photogrammetric results of about 5 millimeters. Then the dense point cloud was generated using the images at full resolution. And in order to avoid precision issues and noise in the upper parts of the structure, we also mask the temple in the higher altitude UAV images. So now I ask Giorgia to start the video of the photogrammetric results.
Yeah, let me see.
Yes.
Okay, yeah.
Okay, thank you. And well, in this video, you can see the photogrammetric workflow and the different products that we obtain from the image-based reconstruction. So we start, as usually, from the structure from motion step, where the camera positions are estimated. In this case, you can see the camera as a blue pyramid, and then also we get a sparse point cloud. Then we move to the dense reconstruction, which provides a more detailed representation of the geometry in the form of a point cloud, of a dense point cloud. And here you can appreciate some details of this dense point cloud. And then from the point cloud, we move to a mesh model. So a triangular mesh, that is a surface made of several millions of triangles that here you can see with a single color. Then there will be also representation colorized according to the norms to the surface. And finally, of course, after this mesh modeling, we pass to the texture mesh. So projecting the images back to the surface that we created, we obtain a really realistic and visually accurate representation of the structure. So here is the texture mesh. And as you can imagine, this level of detail is particularly important for documenting the architectural features.
Yeah, exactly. All the materials, the decay, the damages, and yeah.
Yeah, we need a very high level of detail for these aims.
Yeah, yeah. Let me go back to share your presentation. Thanks for introducing and explain the movie. I should have, yeah.
Here we are, yes.
Okay, so we have seen the approach of the photogrammetry that has been really challenged, especially because, as you explain, the result has to be a very high-level texturized model, but also keeping the architectural details of the temple itself. So now I would like to ask you if you can walk us through the SLAM approach always trying to emphasize how did you use it, and which have been also the, we can say, the plus for your application, but also the limitation.
Well, sure. The entire site was then surveyed again, in this case using a portable laser scanner, and we used the HERON Light handheld system by Gexcel, which is a device equipped with a LiDAR, a sensor, and a inertial measurement unit. And this device was mounted on a telescopic pole carried by the operator, by a single operator, allowing data acquisition simply by walking through the site. So a first trajectory of about 400 meters was performed to cover the entire area, following also closed loops that, as we know, can help then the SLAM algorithm to get high accuracy. And then we perform also an additional acquisition that you can see the trajectory here in red, keeping the sensor tilted in order to better capture the upper part of the structure. So after data collection, that was very, very easy, we processed the data using the HERON desktop software. I think that many of you know this software that is based mainly in three main steps. So at first, there is the odometer stage that estimates the trajectory, integrating the LiDAR and the IMU data. Then the trajectory is divided into local overlapping maps. And finally, a global optimization is performed in order to align all these local maps and to reduce possible drift. So the workflow is largely automatic, except in some cases for the final step where loop closures may need to be manually identified. So here on the right, you can see one of the output of the HERON survey, that is an X-ray orthophoto that allow us to appreciate the completeness of the final point cloud obtained with this HERON device for the whole site.
Yeah, this visualization is really helpful, and that's really amazing. So what do these results tell us about the relative strength of photogrammetry versus SLAM, if you have to like sum up, you know, one against the other, we can say, or better integrated one the other?
Yes, well, once the two datasets, the photogrammetric and the SLAM-based one, are processed, they of course can be compared and integrated after proper alignment. So in our case, the 2-point clouds were first aligned using the well-known iterative closest point algorithm. And since our scanner does not include an RGB camera, we colorized the point cloud, the SLAM point cloud, using the photogrammetric images at first. So the point cloud that you can see here on the right has been colorized after, thanks to the UAV images. And then from these two results, we can for sure observe one of the main advantages of the SLAM-based system, that is a much more complete representation of the scene. Here we can see reconstructed also the trees, power lines, and everything in the site. And this can become even more clearer when we look at these pictures. As you can see here, photogrammetry struggles in area with dense vegetation, of course, or limited visibility, leading to gaps in the reconstruction. On the other hand, the SLAM provides a more complete coverage, but of course, it cannot capture the some part of the structure, the top of the walls, of course. And in addition, the level of detail is generally lower compared to photogrammetry. So we assess also the accuracy of the SLAM data, computing a cloud-to-cloud distance with respect to the photogrammetry model that in this case we can consider as reference. And the average deviation is around 2 to 3 centimeters, so very little, and no major deformation are visible between the two models. However, as expected, the SLAM point clouds shows a higher noise and a lower level of detail, especially on the architectural elements such as the columns, and you can see here in the left image. At the same time, it is important also to highlight that the SLAM survey was significantly faster, both in terms of data acquisition and also in terms of data processing.
Yeah, I think that this really comparison sum up really the advantages, you know, of one technology respect to the other, and especially how they can, and also how they have to be integrated together. So For the second case, Eleonora relocate us to a new site, always in Lebanon, right?
Yes, indeed, after these encouraging results that we get from the first case study, we move to a more complex scenario. So the second case study involves a much larger and a more articulated archaeological site, allowing us to further assess the potential of this approach under more challenging conditions. So the second case study is the archaeological area of Qasr Naous in the village of Ain Akrine, located in the Kura region in northern Lebanon. And the site extends over almost 2 hectares on a hilltop and includes 2 temples dating to the Roman imperial period. So the project in this case required the documentation of the entire archaeological area in order to capture the overall morphology and let's say the spatial relationships with the surrounding. And we need also, in this case, a high-resolution surveys of the 2 temples in order to accurately document their architectural features and their current state of preservation. Indeed, as you can see from these pictures, the Eastern Temple is in a relatively good state of conservation, with some columns still standing, whereas the Western Temple is almost destroyed, with only the elevated base remaining and partially covered by rubble. Despite its worst condition, the Western Temple has a better preserved temenos, that is the holy perimeter around the temple itself, and the area between and around the 2 temples is characterized by dense and irregular vegetation, which partially conceals architectural remains and, of course, prevents direct visibility of the ground surface from an aerial viewpoint. So, given this environmental condition, let's say, integrating aerial and ground surveys was fundamental, and we carried out a campaign, a survey campaign that required 2 days of fieldwork to complete everything.
Okay, so here again, you have used both the photogrammetry and the SLAM approaches. And I think that what is interested is what has been changed in the UAV campaign, but also in the SLAM, respect the previous project.
Well, in this case, we carried out only UAV-based photogrammetric survey, so no terrestrial one. And this survey comprised 3 flights performed using a DJI Mavic 2 Pro, equipped with a 20 megapixel camera. And a first flight was carried out to cover the entire site, acquiring more than 200 images with a ground sample distance of 2 centimeters. That is the flight on the left. And then 2 close-range flights were performed to capture the 2 temples at a higher level of detail. So the Eastern Temple was documented using more than 400 images with an average GSD of 3 mm, and the Western Temple was surveyed through approximately 260 images with an average GSD of 1.3 centimeter. And the 3 photogrammetric datasets were processed separately, using also in this case 3DF Zephyr software, and applying the same standard photogrammetry workflow with dense image matching and mesh reconstruction performed at full image resolution. Given the dimension of the site, photogrammetry required to be properly constrained to avoid deformation in the final model. So in our case, the UAV was not equipped with GNSS RTK for direct image referencing, and high-precision GNSS receivers were not available for ground control points measurement. So we resorted to a classical standard total station survey in order to measure an overall number of 30 targets. And considering the target visibility within the different image blocks, 14 ground control points were used for the processing of the site-scale dataset, while 5 and 6 ground control points respectively were employed for the Eastern and the Western Temple datasets. The remaining survey points were used as common, as independent checkpoints in order to assess the accuracy of the final photogrammetric reconstruction. So coming to the photogrammetric results, at the site scale, a high-resolution orthophoto and a digital surface model were produced. These are products that can support the analysis of the site layout and of its morphology. Despite the considerable extent of the surveyed area, an accuracy assessment carried out on 13 checkpoints shows negligible mean vertical bias and a well-constrained bundle adjustment, leading to a root mean square error of just 2 centimeters. And Note also that in the absence of high precision GNSS survey, after constraining the photogrammetry solution using accurately measured ground control points, we needed to apply an additional rotor translation in order to approximately align the local reference frame to a global coordinate system. So this transformation was estimated using the approximate coordinates of the UAV camera positions provided by the onboard GNSS receiver, and this allowed us to generate approximately the reference final products. Instead of the architectural scale, the close-range surveys produced high-resolution point clouds and texture mesh of the two Roman temples that can be appreciated in this slide. And this model, of course, can be used for detailed architectural analysis, documentation, and dissemination purposes. In this case, thanks to the higher image resolution and the favorable imaging geometry, the temple reconstruction achieved higher accuracy than the side scale results. In this case, we have a root mean square error value of 1.5 centimeter for the eastern temple and 1.7 centimeter for the western case.
So definitely here, the dimension of the site has been also a challenge because, of course, the site has been bigger. And what about the SLAM? I mean, how did the SLAM help you? And also, which differences did you apply respect the first case study that was a little bit, smaller than this one?
Well, as done for the case study of Bziza, in addition to the aerial photogrammetry, we carried out the terrestrial survey using the same HERON light device mounted on top of this telescopic pole and easily carried by a surveyor. And in this case, given the considerable extent of the site, we needed 5 separate SLAM sessions covering both temples and the surrounding archaeological area for a total trajectory of approximately 3 kilometers. So nevertheless, the survey could be easily completed by a single operator in approximately 2 hours. And as you can see from these images, during data acquisition, particular care was taken in order to provide sufficient spatial overlap between consecutive SLAM sessions. This to ensure a robust global registration during the subsequent integration stage. So each session was first independently processed using the HERON desktop software, as previously done for the Bziza case. And then we merged the 5 point clouds using the reconstructor software, obtaining a final point cloud of over 500 million points. So the 5 point clouds were initially aligned pairwise using the iterative closest point approach. And then this step was followed by a global adjustment, simultaneously considering all possible point cloud pairs to minimize residual misalignments and improve the overall geometric consistency of the final model. At the end, the complete point cloud was aligned to the side-scale photogrammetric dense cloud, also in this case using ICP, in order to have a common reference frame among all the survey products. And thanks to the SLAM survey, we obtained a complete three-dimensional representation of the area at the landscape scale. And one of the main advantages of the SLAM approach was the ability to capture the ground geometry, even in densely vegetated areas, enabling also the derivation of a digital terrain model, that is the one you can see on the bottom right. Of course, this DTM couldn't be obtained from the photogrammetric data alone. And we can see also from the 2 vertical section that the cross section that the terrain morphology beneath the canopies was accurately captured in areas that are not visible from an aerial viewpoint. So SLAM was essential to have a complete reconstruction of the ground morphology. For what concerns the accuracy of the point cloud that we obtained from the portable laser scanner, this was assessed using independently measured topographic points. And in particular, we performed a point-to-point comparison in the vertical direction, computing the elevation differences between each topographic point and its nearest neighbor on the SLAM point cloud. So the same analysis was then applied also to the side-scale photogrammetric cloud in order to provide a consistent reference. So the histograms in the slide show the distribution of the vertical discrepancies, and we can see that the SLAM-based dataset has a mean vertical error of 1.2 centimeters, so mean error that is very, very low, with a wider dispersion than photogrammetry and maximum deviation of up to 20 centimeters at the survey boundaries. And moreover, we perform also cloud-to-cloud analysis at the temporal scale, yielding a standard deviation from 3 to 5 centimeters. So we can say that these results are in agreement with the values reported in the literature for first generation handle system as the one used in this study. In this case, as a final step, the point clouds derived from the different survey techniques were integrated in order to exploit the advantages of each surveying method. So in particular, within the temporal areas, the SLAM data were replaced by the high-resolution photogrammetric point cloud. And as you can see from this figure, the resulting model guarantees a complete 3D representation of the area, combining full site coverage provided by the SLAM device with detailed architectural information that are provided by photogrammetry in correspondence of the temple.
Yeah, so also in this project, which has been, I mean, bigger in terms of dimension, we can say that we have been in the same accuracy also because, as you said, that was a system with a local accuracy of about a few centimeters. So, I mean, all the comparison respect also the local accuracy of the system itself.
What we expected.
Exactly, exactly. So I think that it has been very, very interesting work in both the two cases, also starting from we can say the smaller temple up to this huge area. And I'd like to ask you this, you know, to close this discussion. If you would have to sum up, you know, the main lessons that you had from this experience, what you can tell to us, and I'd like also to ask you which might be the advices in case, you know, someone has to approach a project like this in terms of challenges and, you know, conditions. So which kind of advice and also which kind of suggestion you would like to provide in terms, hey guy, you have to pay attention to this because you might you know, encounter this kind of problem?
Well, for sure, I think that these two case study, the case study of Bziza and Ain Akrine, shows that these hybrid photogrammetry and SLAM surveys enable effective multi-scale documentation of large and morphologically complex sites, even under challenging environmental and logistical conditions. And the two techniques, I think they are complementary. So photogrammetry ensures high geometric accuracy, detailed surface modeling, while the portable laser scanning guarantees complete spatial coverage. And so if you need also reliable ground modeling in vegetated areas, you need such an approach. And well, from a broader perspective, we can say that dense vegetation, of course, strongly favors the adoption of LiDAR-based solution. From the aerial viewpoint or from a terrestrial viewpoint, as in the case of the SLAM system. For sure, the availability of the DNS positioning would simplify all the survey, the topographic control, and also the final georeferencing. This can be an important aspect to take into account. And well, in the end, we can say that we need, for sure, carefully planned multi-sensor approach. If you need, let's say, some robust and versatile products, you need to resort to such an hybrid approach. And then what you get, what you obtain, is something that can be useful for several applications, from archaeological analysis to site management to long-term consolidation, and also to public dissemination. So an approach that can be applied to a wide range of application and cultural heritage context.
Yeah, and this is what exactly is important. Also, the last thing that you said. So we are. I think that we are saying more and more that the 3D data is something that is something dynamic. It means that it's something that has to provide you and share information, because it's a data that has to be used by different kind of professional, and also not only professional, also people, for example, who had to make, like, as you said, cultural dissemination. So I'd like to see, you know, I am planning my journey, my trip, and I want to see, for example, how the site looks like, having an overview, also, you know, for dissemination of cultural information. For example, you can populate also this 3D data with information like material, history, pictures, and what else. So really, I think that this possibility to integrate different technology, today we have seen the integration of photogrammetry and SLAM, but just thinks also about, you know, integration of TLS with SLAM, with photogrammetry, is definitely, I think, the key point that really makes the difference, especially in this complex case. So I really like to give a special thank you, Eleonora, for sharing this amazing experience with us. And that has been really, really, I think, great. And I'd like also to thank everyone who has joined today and follow this session. So it has been a great pleasure having you with us today. Feel free to stay in touch with us, with Eleonora, if you would like also to have more details about her experience or also other experience, because as you have seen, she has a huge background in this case. So she will also be able to provide further details, advice, experience also in other cases. So guys, follow us on our social media for update or upcoming events. And we will remain also for a little while longer if you have any questions. So feel free to chat with us. So really, thanks a lot, Eleonora, for this.
And thank you all for the attention. Let me thank also my co-authors, Marco Iamoni, Riccardo Valente, and May Haider. It has been a real pleasure working with them on this journey.
Okay, that's great. Thanks a lot. We can jump directly into the questions. Okay, this is a nice question. Would you have been able to do a reliable survey of one of the temple with just HERON light and no UAV photogrammetry?
Well, from a geometric point of view, we know that we can get a limited level of detail. So only with HERON we can achieve a scale of representation that is 1 to 200. Let's say 1 to 100. So we cannot get all the details that are required in some applications. So I think that photogrammetry in this case, thinking about the columns and all the architectural details, photogrammetry is the best solution, or otherwise also TLS, of course, but this is another survey techniques, another instruments, and it's not easy to have everything with you. Especially in some places, as can be also the Lebanon. So in this case, I think HERON alone would not. We cannot get enough detail for some application. But we still obtain a complete survey of the temple. And if you need, let's say, a level of detail that is 3 to 5 centimeters, that this can be enough for you. So as everything, as every survey, I think that it depends on the final application and what you need, what you want.
Exactly. And yeah, totally agree. This is also what normally we always say also to our students, you know, every survey is a case by case, and especially you have to be clear which is the final goal of your survey. Yes. And so you can calibrate the different technology, respect the final goal. I have another question, Eleonora. What is your preferred method for sharing the final texture model with archaeologists, conservators, or other stakeholders who need to inspect the site in detail?
Well, here depends also on, I mean, how the counterpart, the archaeology, is, if it is able to work with a 3D model. So directly with a 3D model. But I think that in these cases, for sure, also two-dimensional products are important. So orthophotos and two-dimensional two-dimensional output are very important for them. And then we share, of course, also the mesh model, the texture model that we know that requires a lot much more computational effort, let's say, also for the visualization. So in many cases I need to downsample the mesh and the texture mesh before giving them the result. Otherwise it is really difficult for them to have access to the very detailed model. What I can suggest is also giving them also two-dimensional products. They are really important for them.
Yeah. And what you said about the sharing of the texture model, I remember that sometimes can be struggle, not only if you have to share, archaeological side, but also just talking about architectural in general.
Yeah.
Also people who work in 3D Studio Max. So you have to sample the number of the triangles, but of course, the goal is also keeping the details along the edges and discontinuities, because you can sample continuously, but of course you lose details. So this is another thing. Exactly.
Yes. And I think that also a very interesting product is the X-ray orthophoto that we can generate with some software. And it is really useful because you really have an orthophoto, but you have also some the possibility to inspect some stuff that cannot be seen in a normal orthophoto, in a photogrammetric orthophoto. So it's really an interesting product for the end user.
Yeah, also because I think that is something very easy also to share, the data, especially with people who are not expert in 3D, because they can also get, immediately measurement, area, understand everything. So
and import in a CAD environment and draw directly on these kind of output.
Exactly. Another question, how you combine UAV photogrammetry and SLAM? I mean, how did that work in practice? You work in the same software, or how did you do that?
Well, that's a good question, because the integration is not completely straightforward. So the key step is definitely the alignment. In our case, we work within Reconstructor software. So we used an ICP-based approach to bring the 2-point clouds in the same reference frame as a very first step. And then once the alignment is done, you need to do some manual work, because in our case, we essentially replace the SLAM data with the photogrammetric data in areas with higher detail, where higher detail is needed. So I think it would be really interesting to explore, and also maybe to implement some tools that could automatically select the best parts of each dataset and make this process more efficient. This is something that, in my personal opinion, is still missing.
Yeah, no, thanks a lot for your suggestion. It's true that there's the possibility to use also this UAV as constraint inside the HERON desktop software that you mentioned. You have mainly two software, HERON desktop and Reconstructor for advanced analysis. In HERON desktop, you can put different kind of scans, like for example the UAV, and use them as constraints. So you can optimize the HERON trajectory onto the point cloud. But as you rightly said, it's not possible to say, okay, I have this, I want only, I don't know, to use this part of the column, of the area of the temple, and this suggestion might be pretty helpful, instead of using, millions of points as constraint, just using part of them. So definitely. Other questions, if we think about the field work, what were the biggest challenge that you face on site, and how did those conditions change the approach that you had in the data collection? You have explained something, respect also the two cases, but if you might, I don't know, give more details on that, which have been the main challenges in that, and how did you, jump this?
Yes, well, in these cases, one of the main limitations was the lack of high precision GNS equipment. So we were not allowed to use such instrument that is a common instrument in our fieldwork usually, but in this case we didn't have the possibility to use them. So we had to resort to a classical topographic survey, and in addition, also due to some logistical constraints, we could use only small UAV platforms. So no LiDAR on UAV, no UAV, big UAV, let's say, that can help during the flight phase. So we need to use some small, let's say, instruments and easy to be carried in the on site. And so for sure, these conditions influenced how we approach the survey in this case. But at the same time, this is exactly where the advantages of the SLAM system becomes more clear, because SLAM is fast, can acquire continuous data, and does not require, of course, GNSS. So it is easy to use and ready to use also. So these difficult conditions are, let's say, the best condition for the SLAM. And
Yeah.
We can say that, yes.
Yeah, you're right. And also, I would add, when you explain that you have worked for 7 kilometers in the second case, maybe
for 3 kilometers, so 3
3
kilometers,
kilometers and half. Yeah. So I would add that this kind of technology also help us, to stay, in a very good shape and good condition, because you have to walk sometimes also, in narrow place, and so.
Yes.
We can say thanks to this technology that allow us, to always keep in good condition and health condition. Yeah. Okay, so I think that our time has finished. I really want to thanks again, Eleonora, for this experience. Really, guys, if you have other question, details, feel free to contact to address directly her. Thanks all the attendees to have been with us today. Guys, you will receive the record of the session. Eleonora, once again, thanks a lot. Really.
Thank you for the invitation. It was a pleasure for me.
Thank you very much. And well, we will stay connected, and hope to see you again in other event. And of course, we will meet also in other occasion.
Thank you.
So, thank you very much. Have a great day, everyone. Bye-bye.